Let us begin. I'll begin with a word of prayer. Heavenly Father, we thank you for this day, and I thank you for the students. Just pray you'd encourage them to keep working on this class and just stick with it, and that you be glorified in what we do this day, Lord. In your name I pray. Amen. Phew, yes, 12. All right. It's worried me a little bit here. So we will continue today talking about power series. So what I basically told you last time, I can summarize briefly. What did we learn last time? We learned that if f of x is equal to the sum, right, n equals 0 to infinity of a sub n times x minus x naught to the n, then f of x is a power series centered at x naught with coefficients a sub naught, a sub 1, and so forth, right? Now, what did we do last time? For the most part, I just looked at how to study the domain of such a thing. We figured out that if you're given a power series, these are real numbers. If you're given a power series, the domain of the power series has to be an interval of real numbers, a connected subset of real numbers. It's either got to be just a point, right? It could be the whole real line, or it's some finite interval, which is either open, closed, or clopen, or opposed. No, half open or half closed. I mean, some people do talk about clopen sets, but it seems silly to me. It's closed and open, it's clopen. Stupid. I can't say it. So what I want to look at today is, I'm going to less focus on the issue of domain today, and I'm going to focus more on calculations that we can do with power series. All right. So the theme for today is how to manipulate. And so I want to talk about how to manipulate power series. So before I really get into that, though, I first want to talk about what the coefficients mean. All right? So what's the significance of the coefficients? What's their interpretation? So that's the first thing we should talk about. What do the coefficients a sub 0, a sub 1, so forth and so on reveal about f of x, which is given by a power series? So to do this, I need a theorem, all right? And the theorem that I need, when I'm not going to prove it, at least not today, maybe someday, but not today, is that if we calculate the derivative of a power series, all right, that this following calculation actually makes sense. And there is something to prove here, but I'm not entirely sure that the proof is that relevant to this course. I mean, the proof to this, in some sense, belongs in a higher course, admittedly. N equals 1 to infinity. Well, sorry, one more step. N equals 0 to infinity. And so you can bring the derivative inside. And if you bring the derivative inside, what do you get? I'm giving you a heuristic proof that's not really a proof. So I mean, this is basically the idea is I can bring the derivative inside the sum, and since these are constants, right? A sub n is a constant, no dependence on x. You can pull that out of the derivative, right? What do you get? Sum n equals 0 to infinity of n, a sub n times x minus x naught to the n minus 1, right? But how about n equals to 0? What happens with n equals to 0? well, not division by 0, but multiplication by 0, which is what? Don't think too hard. It's just, what is it? You know, I take anything multiplied by 0, what do I get? A 0, yeah. So we can drop 0 from the sum without loss. So this is sum n equals 1 to infinity of n a sub n times x minus x naught to the n minus 1. So there you go. This is our theorem that I'm referring to, which is really just a calculational. So I'm giving us this license to do this, all right? Admittedly, there's a gap in my proof. But this is in fact true. You can term by term differentiate a series, and it gives you the derivative of the series. There's also term by term integration, but I'll talk about that later. Okay, so this, what I just boxed, is really what I need. So let's assume that f of x is equal to the sum n equals 0 to infinity of a sub n times x minus x naught to the n, all right? What we figured out last time is that f of x naught was equal to what? We noticed this yesterday. I was about to say it was 0, and Nathaniel called me on it. He's like, wait a minute, n equals 0. Then if n equals 0, then x minus x naught. It's helpful to actually write out this in an expanded form for these discussions a little bit. So it's easier to see in that notation. What happens when we put x equals to x naught? The rest of it truncates, right? Everything's 0 except for the first term. So that's a sub naught. Okay, differentiate. Then we get f prime of x is what? So all this thing says is that you differentiate term by term. So actually this would be like a1 plus 2a2 x minus x naught, you know, plus 3a3 x minus x naught squared, and so forth. That's all that formula says. And so f prime of x is what? It's a1 plus 2a2 times x minus x naught, right? I'll keep one more term just to help me in the next calculations which follow a little bit below this. All right. So now I think you know what I'm going to do. Maybe you know. We've already figured out that the meaning of the first coefficient, the a sub naught, is the value of the function at the center, right? And if you plug in f prime of x naught, what do you get? See, that's 0. That's 0. Everything's 0 except for the first term, right? So f prime of x naught is a1, right? I think you know where maybe you know what I'm going to do. What am I going to do next? Yeah, differentiate again. So much fun. We can't stop but doing it. And so your f prime of x is so that gives us 2a2 plus 3 times 2 a3 times x minus x naught. And if I was to keep the next term, it would be what? It would be 4 times 3 a5. Sorry, a4 x minus x naught squared, right? If I was to follow that term, that's where that would be at this point. So what's f prime prime? Right, f prime prime of x naught is 2a2, right? So I'm looking for a formula for a2, so therefore a2 is 1 over 2 f prime prime of x naught, right? I think you know what we're going to do. Differentiate again, right? What's that? Oh, this means therefore. It's not a curse mark. Oh, that's just a label, like x. I mean, it could be x sub 45. It's just it's a label. It's a fixed point. Yeah, x sub 0, x sub naught. Could be 3, could be 4. It's just not a variable. It's a fixed point given to us. It's the center of the series we're studying. A lot of times it's equal to 0, but we looked at other cases yesterday. Yeah. If x sub naught is equal to 0, then we're looking at a Maclaurin series, but it doesn't have to be 0.
But x naught doesn't usually equal 0?
X naught could be any number that you like, yeah. Is it usually 0? I mean, it could be. It doesn't have to be, right? I don't know. I'm not sure where this conversation is going. All right, so I'm going to differentiate again, as I don't see there's anything much more to say in that conversation. F prime 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 of x is what? You got your 3 times 2 times a sub 3 plus what? 4 times 3 times 2 a sub 4 x minus x naught plus dot dot dot, right? So if you evaluate the third derivative at x sub naught, what do we get? Right, we get 3 times 2 times, I'm going to write it as 3 times 2 times 1, a sub 3. I mean, just, my point is that really we got a sub 3 is equal to 1 over 3 factorial f prime 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 of x naught, right? And you see where this is going. I mean, if we differentiate again, what happens with the next derivative, the fourth? Now, the fourth derivative, we express like this. This is f parentheses 4. This means the fourth derivative at x is equal to, well, it's 4 factorial times a4 plus, well, 5 times 4 times 3 times 2, a5, x minus x naught. That's waiting in the wings to appear. But anyway, the point is, by this direct calculation, you can see that the fourth derivative evaluated at x naught is 4 factorial times a sub 4. So therefore, a sub 4 is 1 over 4 factorial, the fourth derivative of f at x naught. I think we can see the pattern at this point, right? What's the significance of a sub n? I think I agree with what you said. Let's see here. Give me a second. So you can fill in the blank here. If this, then a sub n equals to what?
1 over n factorial multiplied by f to the nth derivative.
Yeah.
Times x naught.
Yeah. Well, of x naught, but yeah.
Yeah. Oh, that's okay.
Yeah, of x naught, not times x naught. These are all evaluation at x naught. It's, yeah, I mean, this confusion is unavoidable, unfortunately. So the significance, okay, let's just, is this surprising? This really shouldn't be surprising to us at all. What is a power series? In some sense, it's, I mean, not in some sense, it is an unending polynomial approximation to a function, right? So what I'm saying is that if we look at f of x, we can look at it as f of x naught plus f prime of x naught times x minus x naught plus 1/2 f prime prime of x naught times x minus x naught squared plus 1 over 3 factorial f prime 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 of x naught times x minus x naught cubed plus dot, 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 dot. Now, let's just, interpretation, I mean, what's going on here? If you put y equals to this, right, is what? We studied this last semester, right? Well, not me. I haven't taught Calculus 1 in a number of years. But that's the tangent line, right? So if you were to graph f, right? So this would be, there you go, that's y equals to f of x naught plus f prime of x naught times x minus x naught. That's the best linearization to the function at the point of tangency at x naught, right? Then what about the first three terms? What's that? Well, that's the best quadratic approximation to the function centered at x naught. So if I was so foolish as to try to graph it, it would be, you know, something like, I'm not sure exactly. It is not quite right, but I'm not good at the graphing by hand, but that would be these three terms, right? Yeah.
Would the third derivative be like a cubic approximation?
Right. If we include the third term, then that's the best cubic approximation. So there's a definition we can make, which is that given, let's say given g of x, so this is some smooth function at x naught, you can construct what's called the Taylor polynomial for g. So let's say t, I'll put an upper g, I'll put a lower n, would be the sum, well, let me call it k, lower k. So sum n equals 0 to k of the nth derivative at x naught divided by n factorial times x minus x naught to the n. So this, and I should really put an x dependence over here. This is, so I can be a little bit more explicit. This is g of x naught plus g prime of x naught times x minus x naught, and so forth until we get to 1 over k factorial, the kth derivative at x naught of g times x minus x naught to the k. So this is called the kth Taylor polynomial. Generated by g at x naught. Your book probably has some different notation for it. So you notice that what I just boxed and defined, I'm not assuming from the outset that g is a power series there. Like we could construct a Taylor polynomial for a function that's not given as a power series, right? But if you think about it, if that function has a power series that represents it, all right, then the meaning of the coefficients has to be, you know, evaluation at the center, the first derivative, the second derivative divided by 2, and so forth and so on. So if a function has a power series representation, then the meaning of the coefficients is given to us by derivatives of the given function weighted by these factorials. Not all functions have power series representations. All right. Like you could have a function with a piecewise discontinuity. You know? So if you try to calculate the Taylor series for something where you can't differentiate, it's kind of hard. Right? Like take a function with a jump. Try to calculate the Taylor polynomial at the jump. You can't differentiate there, so you can't construct that. Right? Be like, well, then if the function's continuous, surely we can find the power series for it, right? No, there are examples of functions which have infinitely many derivatives, and yet the power series does not match the function. Those are so-called non-analytic functions. I can draw you a graph of what happens. There's a function that looks kind of like this. So here's my y equals to g of x. And if you look at this point, which is 0, all right, the function is so smooth at 0, it's so smooth at 0 that its value is 0, its first derivative is 0, its second derivative is 0, its third derivative is 0, its fourth, all of the derivatives are 0 at 0. And yet the function is non-zero if you just scooch just a little bit to the right of the point. Arbitrarily, in fact, you can, no matter how close you get, you can always find non-zero values to the right of the point. What's the graph of the Taylor polynomial generated by this function? For any k, it's always the 0 polynomial. So the Taylor series, you could say the Taylor series for g of x is just the limit as k goes to infinity of the Taylor polynomial of x. You just take the limit as k goes to infinity. You take a polynomial with infinite order as a power series, essentially. So my point to you is this thing, if I could graph it in green, well, that would just look like this. Right? That's your Taylor polynomial. The Taylor series generated. Taylor series generated by this g at 0. So, you know, Taylor series is not a good tool to study this function at 0. This graph that this black function I'm looking at is an example of a non-analytic function. The formula is something like this. It's 0 if x is less than or equal to 0, and it's like e to the minus 1 over x squared or something like that for x greater than 0. It's something like this. As x goes to infinity, it goes to 1. But as x goes to 0, this goes to a very, 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 very negative number, which means this approaches 0 from that way. So they glue together smoothly, actually, at 0. Yep.
Can you go over the notation real quick? So it's Taylor series G of something?
This, yeah, I mean, I'm saying this is the Taylor series generated by G.
Taylor series generated by G.
Yeah.
So what about that little, sub k over there?
That's the Taylor polynomial. See, polynomial, which means finite, whereas series, not finite. Here, let me be less abstract and give you guys a few examples. So we'll look at G, and we'll look at the Taylor series generated by G of x over here. And what I'm going to do is I'm going to do the scratch work over here, and I'm just going to keep putting answers here and putting scratch work over there, all right? So let's look at g of x equal to, well, e to the x is a good place to start. And what we're going to do is we're going to put x not equals to 0, because I sense that you guys want to do that. So we'll put x not equal to 0. That'll make our life a little bit easier, right? So what's the Taylor polynomial generated by e to the x? It's supposed to be g of 0 plus g prime of 0 times x plus 1/2 g prime prime of 0 times x squared 1 over 3 factorial g prime prime of 0 times x cubed, and so forth, right? I'm going to leave that there. So what happens with e to the x? If g of x equals e to the x, then what's the nth derivative of the exponential? Exactly, this is e to the x again, right? So what's that make the what's the Taylor polynomial work out to then? So what's gn of 0 then? The nth derivative at 0? Yeah, it's just 1. So that gives us that e to the x is equal to 1 plus x plus 1/2 x squared plus 1 over 3 factorial x cubed, and so forth and so on. All right. I'm going to include over here the nice general formula for it, which is the sum n equals 0 to infinity of x to the n over n factorial. Yep.
So do you want us to write out like the first 5 terms or so and then generalize it with the series?
I mean, it depends on the question, but sometimes the first 3 terms is good. I mean, there's nothing written in stone about how much you have to write, but you should write enough that you can illustrate that you understand, right? Let's see here. The next one I would do, how about, what about, say, g of x equal to, sine x is a nice one, right? Sine x is an important function. What happens with sine? So if g of x equals to sine x, then g prime of x is what? And g prime prime minus sine, and g prime 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 minus cosine, and g prime 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 of x, sine of x again, right? So there's this sort of fourplicity, right? I mean, you could write down that this equation is true, right? We could write that g to the 4 times j plus k of x is equal to g to the k of x. Whatever happens at the kth derivative happens at any, if you add any multiple of 4 to that, it's the same thing again. But anyway, more to the point, only some of these are non-zero, right? Which ones of these, if we evaluate at 0, are non-zero? Yeah, we got this one. We got that one, right? So let's see here. We're going to have g prime of 0 equals to 1. G prime 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 of 0 is minus 1. Then what's the next one? Yeah, the 5th derivative. Maybe I should use the parentheses notation, right? 5th of 0 is 1. And then we go back to minus 1. We go plus, minus, right? If you could think about this calculation. So let's see here. We can see a pattern, right? G of 2n plus 1 of 0 is just equal to what? 2n plus 1 is an odd number, right? That's what we're trying to see, the pattern for the odd derivatives evaluated at 0. Minus 1 to the what? N or n plus 1? What do you guys think? But n equals to 0 gives me what here? 1, right? So look, n equals to 0. This is n equals to 0. So I want minus 1 to the 0, which is 1, right? This one is n equals to 1, right? Because 2 plus 1 is 3. I want that to give me a minus 1. Minus 1 to the 1 is minus 1, right? This one's n equals to 2, because 2 times 2 plus 1 is 5. So minus 1 squared is, that's the pattern. So there we go. Sine of x is equal to, apparently, x minus 1 over 3 factorial x cubed plus 1 over 5 factorial x to the 5th plus dot 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 dot. And we can write that as the sum, n equals 0 to infinity, of minus 1 to the n over 2n plus 1 factorial times x to the 2n plus 1. Questions? So I'm going through these because we're going to want to review. These are things you need to memorize. What I'm deriving right now, you need to know these. These you should commit to memory because we'd like to use them for other examples without doing this every time. Actually generating the power series function from the Taylor series is very arduous and kind of, well, boring, really. But it's an important thing for us to go through. And so, but once we have it, then we can use it. So like, how about cosine? It will be similar to sine. Right. Let's see here. So we have g of x is cosine x, g prime of x minus sine x, g prime prime of x is what? Minus cosine x. Third derivative, yeah, sine. Fourth derivative, we're back where we started, right? So you can see g of 0 is 1, g prime of 0 minus, well, 0. G prime prime of 0 is minus 1. G prime 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 of 0 is 0. The fourth derivative at 0 is 1 again. So the pattern appears much the same. Like you guys said, it's very similar to sine. But cosine is in fact 1 minus 1/2 x squared plus 1 over 4 factorial x to the 4th plus dot 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 dot. And we can write its general summation formula as sum n equals 0 to infinity minus 1 to the n over 2n factorial x to the 2n. That 2n factorial and that 2n plus 1 factorial and the n factorial in the formula above, these are all coming from the derivation we did to motivate the Taylor polynomial, right? We saw that those factorials are appearing because of the successive differentiation and evaluation that we did earlier in this class. So there you go. Let's see here. Another nice example to know about is g of x equals to sinh. or g of x equals to cosh, guess what happens? I will forego the details, but through a very similar calculation, we get that sinh of x is what? Wait a minute. Yeah, I'm sorry. Don't listen to my thoughts. Wait a minute. How are you listening to my thoughts? Let's see here. N equals 0 to infinity. And this time we just get 1 over 2n plus 1 factorial x to the 2n plus 1. So did you see, how is this related? It's the same as sine. It's just that there's no what? No, yeah, no plus minusing. Yes?
What section of the book is this from? 9.8.
What he said. I'm not really following the book. I will eventually cover what is in the book in those sections, but I am really not following the book linearly here. Cosh x is 1 plus 1/2 x squared plus 1 over 4 factorial x to the 4th plus dot, 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 dot. Again, we can construct that by, we can generate that by the Taylor series. That is the Taylor series for cosh. Anyway, so in the slick notation, this is sum n equals 0 to infinity of 1 over 2n factorial x to the 2n. All right. These are the major examples I think you should just know just cold. Like, you should know these without thinking, pretty much. Now, I'm not saying you do at this moment. I'm just saying it's something you need to try to commit to memory, all right? But, you know, don't be dumb about it. There's like a lot of redundancy here, right? Because essentially, if you remember the power series for sine, then you can figure out what the power series is for sinh, right, by just dropping the plus minus, the minus 1 to the n. And the same for cosh and cosh, right? Cosine and hyperbolic cosine are related also. Is there anything else here that jumps out at you about these patterns? Like, what can we say about, which of these functions are odd? Sine and sinh are both odd. What kind of powers are in the power expansion, the power series expansion? Just odd powers, yeah, right? An odd function will have only odd powers in its power series expansion about 0. An even function will have only even powers in its power series expansion about 0. See both of those things going on here. E to the x is neither even nor odd, right? So it's got powers odd and even, non-trivial, right? Yes?
Should we memorize like the terms, the first 3 terms?
Yes. I mean, you want to be familiar with, you want to be able to rattle off the first 3 terms without a lot of thinking. And you also would like to be able to write down the general formula. Yeah. Different problems demand different approaches. Okay, so, and of course you can see other things at play here too, right? Like e to the x, remember, is cosh x plus sinh x, right? And if you look at the power series for cosh and sinh, what happens when you add them? You get all the x to the n over n factorials, right? From the cosh you get the even, from the sinh you get the odd. Altogether you get the exponential. All right. Okay, so now that we know these, let me show you a very a simple example built over these. So find power series for f of x equals to the sine of 2x, centered at, let's say, x not equal to 0. Now, yes?
So if x naught is not 0, you have to derive it and find where.
That'll be our next example. Next example, I'll put x not equal to pi over 2, or pi or something, or pi over, I don't know, something else. Make it 1 next time. Example 2. Same, but x not equal to 1. And there, that will remind me. Don't worry, that's like a minute from now. Check it out. So all we do is, see, I wrote this down for x, but the same calculation can just as well be done with u. U. All right. So we can make a u substitution. U equals to what for this problem? Right. And that's kind of all there is to it. So sine of 2x is equal to the sum n equals 0 to infinity minus 1 to the n over 2n plus 1 factorial times 2x to the n. This is not a power series, what I just wrote. All right? Yes, thank you. This has no name. This is I mean, you could call this an unsimplified power series, perhaps, but we don't have a power series until we have something of the form coefficients times x to a power. So it's not much that I have to do, but I do need to do it. This is minus 1 to the n, 2 to the 2n plus 1, divided by 2n plus 1 factorial times x to the 2n plus 1. Now there is the complete power series expansion. This is the complete Maclaurin, if you like. Maclaurin series for sine of 2x. Maclaurin series just means centered at 0. So if I ask you for the complete power series, that means you need to work out the arbitrary terms, right? Now I could say, sometimes I say, find the complete power series for whatever, and also find the first 3 terms. So let's also find the first 3 terms. What are the first 3 terms here? Uh-huh. 1 over 3 factorial 2x cubed, right? Plus 1 over 5 factorial 2x to the 5th. And I'll clean it up a little bit. That's 2x minus 8 over 6 x cubed plus 32 over 120 x to the 5th. Da, 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 da. And I guess we could simplify that a little bit better, right? That's what? That's 2x minus 4/3 x cubed. See, I should have left it as, it would have been smarter if I had, if we look at 2 to the 5th over 5 factorial, it's smarter to do it like this, right? That's 2 times 2 times 2 times 2 times 2 over 5 times 4. Can't write 4. 5 times 4 times 3 times 2 times 1, right? You don't really need to write the 1, just saying. So you can see how that cancels, right? Those guys are gone. These two, natural enemy of that one. So we get looks like we get a 4 over 15. And so there you go. There's the first 3 terms of the power series expansion for sine 2x. So if you just take one of the standard functions and multiply the argument by a number, it's pretty straightforward how to find the power series expansion. Yes?
What do you mean by the complete power series?
It's right here. Yeah. It means the whole thing, not just the first 3 terms.
The generalization.
It mean, you have to give a formula for the non-trivial terms in the general expansion. Yep. Pragmatically speaking, it means that you have to give a summation notation formula for it. All right, x not equal to 1. This one's a little bit sneakier. So we're looking at sine of 2x, right? So you got to use your imagination. This is the sine of 2 times x minus 1 plus 1. Don't agree? I added 0. And the reason I did that is just because then that gives me sine of 2 times x minus 1 plus 2. Because I know trigonometry, and that gives me the sine of 2 times x minus 1 times the cosine of 2 plus the sine of 2 times the cosine of 2 times x minus 1. Yeah, adding angles formula. And now I can just fall back on my table and substitution. Anything worth doing is a lot of work. See here, cosine of 2, summation n equals 0 to infinity of 2 times x minus 1 over 2n plus 1 factorial. I'm glad you asked that question, Brian. I would have probably shied away from doing that example today if not for your question. So I appreciate your question. Let's hear. Well, if I didn't do it today, I was going to do it someday. It's not like you're going to. It's part of my ninja way. I mean, it's going to be said. I mean, this is like a standard example for me. But
how do you change your x naught to 1 by doing that? Because can you do that for the rest of them technically? Because where's the x naught equals 1 over here?
well, so what's centered at x naught? Centered at x naught equals to 1 means that you're writing sine of 2x as equal to the sum, n equals 0 to infinity of stuff times x minus 1 to the n. So to make x minus 1 naturally pop out of formulas, you just create it in what you already have. I mean,
when you found the formula, you made x naught was 0. The reason why you use sine to be odd is that's where x naught is not 0.
I'm processing your request. What did you say?
When you found the formulas for all of them, because x naught was 0, only floating 0 because x naught was 0. So does that mean the floating 1 with x naught is 1? Right?
So,
Because like when we did like this stuff, and found like g prime, g double prime, all that stuff, it was of 0. So wouldn't it be of 1 because we're making x not equal to 1?
yes, you could do it that way. There's more than one way to find the Taylor series of a function. I'm showing you a sneaky way. If you wanted to calculate this by, direct application of the Taylor series, you could also do that, right? So maybe what you're asking me is, why on earth did I do this when I could have just done, g of x equals to the sine of 2x, right? So then g prime of x is equal to 2 cosine of 2x, right? And g prime prime of x is minus 2 squared sine 2x, right? And g prime prime of x, prime 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 of x, is minus 2 cubed cosine of 2x. And the fourth derivative at x is, well, it's 2 to the fourth sine of 2x, right? And so from that, I can directly get that I've got, g of 1 plus g prime of 1 times x minus 1 plus 1/2 g prime prime of 1 times x minus 1 squared plus 1 over 3 factorial g prime 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 of 1 times x minus 1 cubed 1 over 4 factorial g prime 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 of 1 times x minus 1 to the fourth, right? Which would actually give me what? That would give me sine of 2 plus 2 cosine of 2 times x minus 1 plus 1/2 minus 4 sine of 2 x minus 1 squared plus 1 over 3 factorial minus 2 cubed cosine of 2 1 over 4 factorial minus 2, well, not minus, it's plus again, 2 to the fourth sine of 2, apologies for my handwriting, it gets bad down here, x minus 1 to the fourth plus dot 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 dot, right? And after all of that, I would have the first 4 terms in the power series. But do I have the complete power series? No. Could you find it differentiating and looking for a pattern? Probably, right? Is that better for you than my method? Possibly, right? But what if I just twist the problem a little bit, right? Like suppose the only way you have to find power series is by application of the, the only way you have to find the power series is by generation of, by using the Taylor series definition, by generating it by differentiation and evaluation. So my question for you is differentiation followed by evaluation always the go-to method for finding power series for functions? What I'm trying to get across to you is it is not. And I don't think my examples yet have shown you why. Because this one you could also do that way. I agree. But this one, and I'll let this one be at 0. Find the power series expansion for this. Well, I can find the first 3 terms without much work. This is x cubed. And so I'll write it up here. Cheat sheet. E to the u, 1 plus u plus 1/2 u squared. So I'm setting u equal to x squared. So this gives me 1 plus x squared plus 1/2 x squared squared. Right? And then so that gives me x cubed plus x to the 5th plus 1/2 x to the 7th. The first 3 non-trivial terms in this power series are given as follows. What if you did that directly from Taylor series generation? What would that look like, the calculation? So this, think about what would that look like if you just, f of 0, fine, well that's 0. What's f prime of x? Right? And then you differentiate again. And then you differentiate again. And then you differentiate again, and again, and again, and you're not going to see a pattern, right? Yeah.
So are you telling us to pull out, is that kind of like why you're telling us to kind of memorize these? So
Yes.
we're able to pull out, so we can pull something out and then multiply it by something?
These are building blocks. We can use these with natural operations to build other power series, is my point.
So if there was like a cosine thrown in there, like a cosine to the x squared, like what if we had cosine 2x multiplied by like some random something, we could just like pull it out and be like, oh, we're actually.
So, I mean, like x plus x cubed, for example.
Yeah, so we could
Right, yeah.
pull out the cosine.
Again, I'm going to find one centered at 0. So suppose I just want to find the first, let's say the first 4 non-trivial terms. Find the first 4 non-trivial terms. So this guy is 1 minus 2x over 2, parentheses on 2x squared.
What makes it less trivial?
1 over 4 factorial, 2x to the 4th. What makes it less non-trivial? It just means non-zero. The first 4 non-zero terms. I mean, if I just said find the, in some sense, some sarcastic students, if I said find the first 3 terms of the power series for f of x in example 3, a certain class of students that I respect would tell me 0, 0, and 0. Because the evaluation, the first derivative and second derivative are all 0. So the second Taylor polynomial of f of x in example 3 at 0 is just the 0 quadratic. They would if I said find the first 3 non-trivial terms. So that's why I say non-trivial. It's to ward against the attack of that sarcastic student. Let's see here. So anyway, and so forth. So we multiply, and how do you multiply a series times something like that? We do it term by term. And so the way that goes is it gets me an x. One more step here before I do any multiplication. Let's clean these up. What's that? That's 1 minus 4 over 2, so that's 2x squared. And that's 1/6. All right, so x is going to give me x times 1. X times this gives me minus 2x cubed. But you notice I also pick up a x cubed from, you got to go order by order here to keep out of trouble, all right? The lowest order thing possible is this x times 1. Right? The next lowest thing possible is this times that, which is cubic. But another way you can get a cubic is from this times that as well, right? You have both of those terms at level 3. So I get my minus 2x cubed, then I get my plus x cubed, right? What's the next order possible? I think it's going to be minus 2x to the 5th, right? But that's not the only one, right? Let me color code here. That's coming from multiplying. This one's coming from multiplying this guy times that guy, right? But we also have this times this to get order 5, right? Which gives me a plus 1/6 x to the 5th, yeah. I've only got the first 3 non-trivial terms. Did I say 4 non-trivial terms? I meant the first 3 non-trivial terms. There we go, okay. So that's something I'm allowed to do, you're not allowed to do. So here, minus x cubed. What's that? Is there an x to the 4th? Oh, that would be up. That would be higher order. That'd be the 7th power. I'm just. Oh. So that's my cubes. The cubes go to there's just minus 1 of them. Here I have minus 2 plus 1/6, which is what? Yeah, minus 11/6.